This is a start to finish tutorial on developing an interactive PID controller. We have the temperature control lab, and it has two heaters. Here is heater number 2 and heater number 1. And we want these to be able to sense what the other one is doing and be able to compensate for that. We're going to set up two PID controllers. Here's PID control loop number 1 and then PID control loop number 2, and then we're going to sense what the other one is doing, temperature 2, and then we're going to use a feed forward controller to then adjust the output 1, and similarly we'll sense what temperature 1 is, have a feed forward controller, and be able to compensate, add or remove a little bit from OP2. So this is going to be an overall view of what we're going to be doing to develop the controller, not just the feed forward control. Let me give you just an overview of what we're doing with the temperature control lab. For controller design, we want to start by selecting the actuator, and that in this case we have Q1 and Q2. Those are two heaters. And then we have our two measurements. We have T1 and T2. If we have data available, then we can do things like graphical fits or doublet tests or pseudo random binary sequence or signal, or get historical data, do a regression. And so in this tutorial we're going to start here at the very beginning. We're going to also just show you a physics-based model, develop our first order plus dead time, and then from that we are going to develop a controller. These are the options for P-only, PI, or PID control. And before that we have a measured disturbance as well, and this is going to give us our feed forward gains that we were just talking about, K feed forward 1 and K feed forward 2. We could do stability analysis as well to get KC limits. We're not going to do that in this exercise. We will use some tuning correlations, ITA or IMC, and then we'll implement the controller and we'll adjust the tuning parameters until we get acceptable control performance. This is the flow chart that we're going to go through. We're going to just start by going down here. There's a script at the very end. If you'd like to follow along on this, there is the link right here. I'll put that in the description of the video as well, and that'll bring open the web page. And if you go all the way down to the bottom, the thing that I'm going to be running through here is this TCLab interacting PID control development and testing. So if you select that, it'll bring up an IPython notebook viewer, and what you want to do is just go ahead and download the notebook. Now this is just the raw text version of the IPython notebook, so if you want to get the IPython notebook and download it, I don't recommend Edge for this one. It doesn't work very well to export it, so maybe in something like Chrome or Firefox. And then if you download notebook, you'll see the text there, but one of the things you can do is just right click and do save link as, and then that will give you the IPython notebook file. Alright, let me just go ahead and open this up and we will go through the notebook. The very first thing that we need to do is collect the data, and we should have already done this previously. But if you need to do it again, you can just collect the data here. It will grab the data. If it doesn't, this checks to see if it exists, and if it exists, then if data.csv exists, then it will already be here and you don't have to run it again. Alright, but we're going to just wait for this to run and collect some of the data, and then once this is done, I'll move on to the next step, which is just plotting the step test data. Has about 100 seconds left to collect all of the data. You can see just scrolling down, you can see the heater values and the temperatures right there, the current temperatures. We'll plot those next, and then we're going to go on to developing a physics-based model. We're just going to run this. You'll have to install Gecko for this exercise. Let me go back to the overview and where we are on this. Okay, so we are first of all collecting some of our data. We're doing some step tests, and we are going to do two things. We'll do a graphical fit and a regression, and then we'll also simulate a physics-based model just to see how those align. We'll get our first order plus dead time model, and then go on down to develop our controller next. The physics-based model is reviewed in other videos, but essentially we're just looking at our heaters and the temperature sensor right there, and we have, in this case, two heaters right next to each other. Alright, and one feels the effect of the other. So if we have temperature 1 and temperature 2, as temperature 1 gets hot, then temperature 2, even when the heater's off, temperature 2 will rise in temperature. And so we want to be able to model this effect because it's going to be important when we have our disturbances. Okay, so temperature 1 is going to be a disturbance for temperature 2, and temperature 2 is going to be a disturbance for temperature 1. If we know this effect right here, then we can design our feed-forward controller. And we'll just put that into our control calculation. Alright, let me come back here and just see how this is doing. It looks like it's almost done. Okay, there it is. It disconnected successfully. Now let's go ahead and just plot the results here. I'll run this next cell, and that will generate the plot. So you can see the values that were generated just in graphical form. Now we're going to run the physics-based model prediction. If you don't have Gecko, just run this. If you do, you don't have to run this cell. It says it's already satisfied. If you don't have permission to run it on your computer, if you have a permission there, you can type --user, and then it will install it locally, so you don't have to have administrative privileges. Alright, if I come down and run this one, it's going to be the Gecko Prediction. Again, if you don't have the data file, it'll get one from this other source, but in this case we generated our own data file. Alright, come down and let's just take a look at our prediction. We have some heat transfer coefficients, we have some heater power values, and then this time constant that is the conduction between the heater and the sensors. And that's reviewed in some other videos. You can see sum of absolute error. It's very good. It's 335. So that's the total absolute error between the model prediction and the measurements. And there are 1,200 points. So on average, it looks like it's off by about 0.25 degrees Celsius, which is a very good prediction. The model is just predicting based on the heater values. All right, let's go on to the next one. We have first order plus dead time parameters, and this is going to be the graphical fit. So we just did a physics-based model. Now we're going to do a graphical fit. Alright, and this one doesn't rely on energy balances, just relies on empirical model. And we have two models. One is the dashed blue line, and the other one's the dashed red line. And as I increase the gain, alright, you're going to see the predictions change. And also increase the tau p value. It looks like I need some dead time because it's leading here. So let's go and increase as I drag it over. You can see it's aligning a little bit better. You can see the absolute error is about 5,000. From the physics-based model, I had about 384, I believe, or 334. All right, let's go ahead and increase this interaction parameter. You can see when temperature 1 gets hot, the actual temperature 2 is getting hotter than it's predicting. So let's increase this interaction parameter. Alright, and you can see that now we're losing some from heater 1, but heating up temperature 2. I'll go ahead and increase this a little bit more. Alright, so you can see I've gotten my integral absolute error down to about 1,000. Okay, you can still play with this a little bit more, increase or decrease some of the parameters. Try to get this to as low of a value as you can. Okay, and so I'm just going to adjust it back and forth until it gets to a lower value. Let's see what I can do here. Oh, I think I had better values before. Okay, that looks pretty good. Let me go just a little bit longer here. Okay, so you can play around with it and try to come up with the best values that you can. Okay, but somewhere around 1,000, that would be very good. 1,000 to 1,500. It means that you're off, you know, about, with the 1,200 points, you're off about a degree Celsius for every data point. So that would be still very good. Alright, let's see, and it isn't showing up here. If you need to adjust that so it shows up on the plot, just put in 2 here for the number of digits it displays, and then it will show up on the plot with more digits. Okay, if I come down here to determine FOPDT parameters with optimization, now I'm not just guessing and checking, but I'm going to let an optimizer do this for me. So I have some guess values. Maybe you put in these guess values from the ones up above, and then here are the parameters that it's going to use to do the optimization. In this case, it's going to be a little bit slower because it's using scipy.optimize.minimize, which is a slower solver than Gecko, but it's able to handle the these dead time parameters better. So use that one instead. So this one's going to go for a little while. You'll see the initial sum of squared errors with our guess values, and then it's going to be optimizing values, and it's just working on that. It'll work on it for a minute or two and then come up with a solution. Okay, but let's go on. While we're waiting for those parameters, we're just going to go on to the next step. Okay, so we did number 1 was the physics-based model, number 2 was the graphical fit, and right now we're just waiting for the regression to finish, and that's going to give us again a first order plus dead time model. Then we want to take and start designing our controller. We do have a measured disturbance, and so let's design our feed forward, K feed forward, and also use our tuning correlations to come up with good Kc, tau I, and tau D parameters. As we go down this list, we're going to be asked if this is an integrating system, and in this case it is not an integrating system, so we can use a PI or a PID controller. We would not want to use a P-only controller because it can lead to offset. So the definition of an integrating system is if we have, for example, our Q1 value, the heat is going to come up, but then it's going to come down when the heater is 0. If it were an integrating system, this value would stay high, kind of like a tank with no outlet but an inlet. Okay, so it's a non-integrating system, and so we're going to use PI or PID control. Let's go back here and just see how it's doing. Okay, so it came up with the final sum of squared error objective of 522. So just a little bit worse than the physics-based model, but still very good. And you can see some of the parameters here that it came up with in the end. Okay, and also the fit. All right, let's go ahead and design the PID controllers. Okay, I'm going to go ahead and run this. It's another widget that you can use. And Alright, so here we have some recommended ITAE parameters for PI control and also IMC for PID control. And those you can find on the course website. Let me come back here. Alright, and if you want to look up those PI or PID control, and you'll see some of those tuning parameters. This is IMC for PI and ITAE for PI control. Or if you want to get PID parameters, just come here and it shows the IMC tuning correlations for PID control. Alright, I've just put those into the code and you can see those correlations. That's where they came from. Alright, so these are the recommended values. It automatically loads those in. Now let's just adjust these because we might want to try to minimize the integral absolute error. Alright, so I'm going to dial this up just a little bit more. Okay, on the KC value, it looks like I want to go down a little bit more on the tau I as well, get there a little bit faster. It looks like that KC is maybe a little bit too high. It's leading to some oscillations. Okay, let me go down just a little bit further on the tau I value. Alright, I'm going to go down to 60. Let's go down to 50. Okay, so that's fairly good. I'm going to reduce the tau D value just a little bit. And let me dial up the K feed forward. I think, okay, minus 0.4. Okay, this looks pretty good. 6,700. That looks like fairly good control. It couldn't do anything about this right here. You know, that's just the interaction between the two controllers. The heater value was at 0 during that period, but it looks like it's doing a fairly good job of tracking the set point. So we started with the ITAE or IMC recommended values, and we adjusted those to try to minimize the integral absolute error between the set point and the PV. So the next thing we want to do is go ahead and test it. And let's just take these 15, 51, 6, and negative 0.4. And we're going to go ahead and test it here by plugging them in to this final area. Alright, so this is going to be, let me get those again, 15, 51, 6, and negative 0.4. And 51, 6, and negative 0.4. Okay, now when you run this, you can run this either in Jupyter Notebook. It's trying to detect IPython notebooks, or you could run it as a script as well, and it should be able to animate the plot if you leave animate equals true. So I'm going to go ahead and run this. It's going to check to see that the temperature is below 25 degrees. If it isn't, then it will wait until it is 25 degrees. It'll check every 10 seconds. It looks like it is, and you can see the integral absolute error starting to accumulate. We will probably get just a little bit higher than our predicted value because we have measurement noise. This is not going to be a smooth response. These are actually being collected from the temperature control lab device. Alright, so here it goes. We have heater 1 turned on to 100%. The set point was changed up to 60 degrees Celsius, and you can see it's trying to get there as fast as it can. You can see the blue line starting to rise, and you'll see as temperature 1 increases, you'll also see temperature 2 start to increase as well because they're located next to each other. Looks like we had a dip in the measurement here, a little bit of measurement noise coming through right behind this legend, but you can see here the animated PID response. Let me go back to, just as this is going, I'll go back to the web page where all of this is located. Again, there's a link to this in the description of the video. So if you come to the temperature control lab, and down at the bottom, this is the interacting or the 2 heater control. And down here we also have a very simple script. If you'd like to try this, it's the simple PID package. I believe they use a different form for the PID controller, the velocity form, but you're welcome to use this as well. Here is how you configure a PID controller 1 and a PID controller 2, and then we're going to loop through 600 times and get our new output values based on the current measurement of T1 and T2. Gives us our output 1 and output 2. This does not include the feed forwards in them, so you would need to add in a K feed forward plus your disturbance value here at the end of your PID controller. Then we're just going to print a line, sleep for 1 second, and then do it all over again. This is a very simple PID controller. It'll give you different results than the ones that we're showing, but it's an alternative if you'd like to use that. The way that we're judging the control performance in this case is we want to quantify things like rise time, peak time, the period decay ratio, overshoot ratio. If we have an oscillatory response, we often use these to quantify the performance, how much overshoot did I have, or how long did it take to decay to the new set point. We'll also use as our performance metric this integral absolute error. We're going to be taking the set point and the measurement at each time point and then just add those up. We want to try to get the best performance possible. Alright, let's go back and just see how this is doing. You can see it got to set point fairly quickly and is coming down. You can see some movement that is here on the heaters, and that is due to the derivative term in our PID controller. So you could improve that a little bit. The fluctuations, if you were to do something like put in a filter for the derivative term, you could get this to be a smoother value. Now in this case you have just transistor heaters that aren't affected very much by turning them on or off. But if you had something like a valve and the valve travel were excessive, then it would be potentially problematic. Okay, we're going to go ahead and pause it here and then pick back up after this is mostly done and just look at our control performance. Okay, just checking in on the performance here. You can see that it came up to the set point for temperature 1. Temperature 2 has come up as well, but didn't quite meet the set point. It was close, but then the set point dropped down to 35. Let's just go up and look at, compare. We have our integral absolute error. It's just crossing 5,000 right now. We're about 400 seconds into it. Now let's just compare our simulated values with what's being produced here. So you can see it looks fairly similar. We're right about 400 seconds. We just had a set point change in temperature 2 or temperature 1. Temperature 2, it came up. You can see it predicted that it was going to barely reach the set point and then start coming down. And you can see the very smooth response on the output. You can see in the what actually happened is it was very noisy here, a lot of fluctuation in the output, and that's due to the derivative term in the PID controller. Okay, that we don't have filtered right now. Let's come down and just take a look at this again. Alright, these two are kind of on top of each other, so it's the one above, you've split those apart into 2. But here you can see we're going to exceed our integral absolute error that we predicted. We're coming up on about 500, but this is still climbing. It might go up to about 10,000 or so. We'll see in the end how this does. Okay, there's about a minute left. You can see that they're both of them trying to reach almost their set points, and to avoid undershoot, they're both giving a little bit of heat even before it reaches that lower set point. So you can see both Q1 and Q2 turning on, and they're going to try to level out at their new set point, and it'll finish at 600 seconds. So we're about 50 seconds or so away from finishing here. And you can see the integral absolute error. That actually it was a little bit lower than I expected. We predicted, I think it was, let me go back up and just check that out on the prediction. Okay, so we predicted 6,700 for our integral absolute error, and in the testing right now we're about 7,000. So not too far off. And it looks like it's going to level out. It's just very minimal error accumulation now because it's reached the set point and is going to be almost zero error from here on out. Okay, so here is our PID controller, and it'll just conclude. Alright, so it's complete, and there were the values that we tested. Okay, so that concludes this notebook exercise. If we want to just go back and review briefly what we just did, we started with our controller design, and we came up with our sensors and actuators. We did all three in this level: the physics-based model, graphical fit, and regression. We came back to a first order plus dead time model. We did not cover a second order plus dead time or time series state space. We could have done this route and done a model predictive controller with our physics-based model, but we didn't do that. Here's a course available if you're interested in that approach. We took our measured disturbance and came up with a feed forward gain, and we figured out that it was a non-integrating system, so we selected one of these. We picked PID control. We wanted the derivative action in there, and then we used the tuning correlations. We did not do a stability analysis. We got our tuning correlations to come up with starting values. We looked at the control performance with a simulator and adjusted the KC, tau I, and tau D, and then implemented it and found that we had very good performance. We looked at the integral absolute error, but you could also look at other things like overshoot, decay ratio, and other parameters if you had some oscillations. Okay, so that concludes this tutorial and overview of how to set up an interacting PID controller using Arduino data to test the implementation.